Right, we've had a look at the mass spectrum of methanol and the mass spectrum of pentene, but some of the most interesting mass spectra that you can come across are the mass spectra of ketones. And so for the rest of this course, I'm going to be concentrating my efforts on exploring the mass spectra of ketones. Of course, when you look at a mass spectrum of a ketone, look at it in the same way as you look at other mass spectra. Look for the molecular ion and look for the base peak. In this particular mass spectrum of 2-hexanone, at this point I really want to explain the base peak. The base peak is at m/z of 43. This base peak comes through a mechanism called alpha cleavage. And so let's have a look and see how alpha cleavage of a ketone is possible. So here's 2-hexanone, and for clarity I've just condensed the formula of the terminal part of 2-hexanone because I'm really interested in the region around the ketone. And what I'm really interested in is this bond alpha to the ketone, and that is the bond that will be cleaved in this mechanism to give m/z of 43. So we know that the molecule contains pi electrons, we know it contains lone pair electrons, and we know that of those two we're most likely to lose a lone pair electron. So under electron impact, it's that top electron that I have allowed to be knocked off. And so as it comes off, we're left with a positive charge here, and of course this here is our molecular ion. So we can confirm the mass of this against the spectrum that we have. Okay, so what happens in alpha cleavage is that one of these electrons in this bonding pair here, in the sigma bonding pair, one of those electrons joins the unpaired electron as sitting on the oxygen, and that gives rise to a triple bond, and of course the oxygen stays on the oxygen. So what happens to the remaining electron? The remaining electron forms a radical, and so we end up with a radical which has no charge, which is not visible in the mass spectrum, and we also see this fragment over here, which you can calculate as 2 12s plus 16 plus 3, which is m/z of 43. So what has happened here is we have got alpha cleavage of the ketone to form m/z of 43. So methyl ketones are particularly easy to see. If you get spectra with mass m/z 43, it's quite likely that you will have a methyl ketone. You can see that however large this fragment, large this portion of a molecule, you'll always form that m/z 43 if the left-hand side is a methyl ketone. Right. Of course, that's not the only alpha bond to the ketone that's present, that there are other bonds. So there's another alpha bond here. So if I knock off the electron on the left-hand side rather, we can draw a similar mechanism for cleavage on the left-hand side, but remember your methyl radical has no charge, so will not appear in the mass spectrum. In this case, the right-hand side is what appears in the mass spectrum, and its charge is 1 and its mass is 85, and so you should see from another alpha cleavage a m/z of 85. Of course, remember that the peaks you see are dependent on the stability of the fragments that are formed, and a methyl radical is really unstable, so we expect to see m/z to be a much smaller peak than m/z 43, because we would have to form a very unstable radical to get m/z 85. So compare these back to the spectrum, and can we see m/z 85? Yes, we can see it, but we really want to explain m/z 43, and both of those can be explained through alpha cleavage, either on the right alpha bond or on the left alpha bond.